Okay, I think we can start. So before the scientific program, let me make a short announcement. So the proceeding of ICMP will appear as a special issue of the Journal of Mathematical Physics. And for this reason, we would like to invite all speakers, so plenary speakers, invited speakers, prize lectures speakers, and also contributed speakers, to submit an article to JMP. We will send probably an email in the next days with more information, but the submission is very easy. The only thing that you have to make sure is that when you submit a paper to JMP, you select the special issue for the ICMP. Good. So that was the announcement, so we can switch back to the scientific program. It's a great pleasure for me to introduce the next speaker, Peter Hintz. So Peter graduated from Stanford University in 2015 with a thesis under the supervision of Andras Vasi. After graduating, Peter spent 2 years as a Miller Research Fellow in Berkeley. In 2017, he obtained a Clay Research Fellowship, and in 2019, he was hired as assistant professor at MIT. I'm very happy that recently, I think just last month, Peter joined the faculty of ETH in Zurich. So now he's almost a local here in Switzerland. Despite his young age, Peter is already a leading figure in the field of partial differential equation, in particular, partial differential equation arising from general relativity. One of his major results was the proof of global nonlinear stability of Kerr black holes on de Sitter space-time. For his many achievements, last year, Peter was awarded a Sloan Research Fellowship. Today, he is going to tell us about microlocal analysis and stability problems in general relativity. So before asking him to start with his talk, let me offer him our plenary speaker medal. So, as a souvenir of his participation to ICMP. So please go ahead with your talk now.
Well, thank you very much for the very kind introduction. Sorry about the change here. All right. Well, thank you very much, Benjamin, for the kind introduction, and of course to the organizers for the very kind invitation to give a lecture at this very interesting congress. So as I was preparing the talk, just like the previous speaker, there were a few iterations, and so ultimately it ended up being more about spectral theory and relativity, but there's going to be a slide or two about microlocal analysis as well. So interest in this talk will be on stability problems in relativity, so more specifically for the Einstein field equations in vacuum. So let me introduce the key player here. So the context is geometrically that of a four-dimensional manifold M, which is equipped with a Lorentzian metric, so like Riemannian, except with an indefinite signature, minus plus 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 on that manifold. And one typically imposes a certain causality condition called global hyperbolicity. But if you don't know what that is, it doesn't matter much here. The Einstein vacuum equation, then, as written down over 100 years ago, simply requires the metric to be Ricci flat. So Ricci curvature of G is equal to 0. And that's something very concrete and explicit. You can compute the Ricci curvature in local coordinates, and it's an expression involving up to second derivatives of the metric and also nonlinear terms, such as the inverse metric appearing and products of metric, inverse metric, and so on. Of course, the phenomenology associated with this equation, especially if you also allow for a non-zero right-hand side, which would model matter in the universe, is of course very well known and much studied in astrophysics, cosmology, and so on. But even in vacuum, already the theory is extremely rich, describing things such as black holes, which will be the focus of my talk, or gravitational waves, which will also appear in the form of solutions of the linearization of the Einstein equation. There also exists a version of the equation which Einstein introduced and then disregarded, but now it got new life, which includes a cosmological constant lambda, which is just a parameter of the theory. And according to physicists such as Rees, Perlmutter, and also the Nobel Prize Committee, in the actual universe, this cosmological constant indeed attains a small positive value. And so it will turn out that mathematically, actually, the positive lambda case offers many conceptual and geometric simplifications. So this is the equation of interest. So let me introduce a few simple examples. The earliest one was even written down before the theory of relativity, general relativity, was devised. It's Minkowski spacetime, so that's just the four-dimensional manifold R4. and the metric is just the flat metric, just with the 1 minus sign compared to the usual Euclidean metric. The next interesting example is due to Schwarzschild in 1916. And so I write down the metric explicitly just for your amusement to illustrate that it's actually an extremely simple metric that can be found just by imposing spherical symmetry and calculating Ricci tensor and making it be equal to 0. And so this solution actually depends on a parameter m, which is real, but typically for physical reasons taken to be positive or non-negative. And it encodes the mass of a black hole. So why does this metric encode, so describe a black hole? At the bottom of this slide, I have a little figure indicating that. So what's drawn here is a collection of 5 light cones. So at various points in this space-time, I'm only keeping track of the radial coordinate, which is roughly the distance to the central singularity of the black hole, and a certain time coordinate v. And so the 2 spherical directions are suppressed. So at each point here, I draw the light cone, which is the collection of tangent vectors at that point, whose squared length is equal to 0. So these are the tangent vectors of trajectories or world lines of massless particles in the theory. And massive observers, such as myself, have to move upwards in the interior of these light cones. And so you see here that if you find yourself, unfortunately, on the left-hand side of this hypersurface r equals to m, then as a massive observer, you have to follow these light cones in this interior upward direction, and you cannot escape to the outside region anymore, and you cannot escape to infinity either. Whereas if you start on the right-hand side of this hypersurface, then you're free to go where you want. So that's exactly what makes r equals 2m as a hypersurface, the event horizon of a black hole, the point of no return. Once you're on the left-hand side of it, you cannot escape to infinity on the right-hand side. Okay, so it's an extremely remarkable fact that the second simplest solution of these Einstein vacuum equations in fact describes black holes. I always find this quite amazing. Some almost 50 years later, Roy Kerr found in 1963 a generalization still of the Schwarzschild family of metrics, which also allows for the black hole to have angular momentum, so they're no longer spherically symmetric. It's an explicit formula, but a little bit complicated, so I'm omitting it here. Now, all of these spacetimes that I just described have the feature that they are so-called stationary. So very concretely, the coefficients of these metrics are time independent. But of course, the actual universe, for instance, by virtue of me giving a talk here, is certainly time dependent. And the typical way one can start analyzing time-dependent solutions of these equations is by studying the initial value problem. So I already mentioned gravitational waves, and so it turns out, in a way that I'll explain a bit more, that the Einstein vacuum equations indeed have the character of a wave equation. So like any good wave equation, you have an initial value problem where you have to specify sort of the initial amplitude of the gravitational field, quote unquote, and the initial rate of change of the gravitational field. So more precisely, the initial data for the Einstein vacuum equation consists of a 3-dimensional manifold, say time equals 0, you freeze your universe then, a Riemannian metric gamma on this 3-manifold sigma, and a symmetric 2 tensor on sigma, and they have to satisfy a certain compatibility conditions called constraint equations. The task as an initial value problem solver for you is to find a space-time globally hyperbolic, which of course is supposed to satisfy the Einstein vacuum equations, so here with cosmological constant if you want. And moreover, you want to embed this hypersurface sigma as a space-like hypersurface inside your 4-dimensional space-time M, such that the induced metric on this hypersurface is equal to gamma, and the extrinsic curvature, the second fundamental form of this hypersurface as it sits inside the ambient space-time, is given by K. And it's a fundamental theorem from the 50s due to Cheguebreha and then sort of globalized by Geroch in '69, that there exists a solution of this equation, in fact, a maximal globally hyperbolic development, I'll just say maximal solution here, of this initial value problem, which moreover is unique up to the natural symmetry of the problem, namely for any diffeomorphism phi of this manifold M, you can just pull back the metric G by this diffeomorphism, and it will still satisfy the Einstein vacuum equation. That's sort of the general covariance of the theory. But it takes a very simple mathematical form here. Okay, so with this initial value problem now you can start studying stability problems, and to explain what they are, Let me just do this by way of example. So this celebrated theorem by Christodoulou and Kleinerman from 1993 concerns the stability of Minkowski space. So in this case, the initial surface sigma is just R3. So imagine T equals 0 inside of R4. And the initial data gamma and k are now assumed to be close to the Euclidean metric on R3 and the 0 tensor. And of course, the closeness is measured in a particular function space on weighted Sobolev space. And the theorem then states that the maximal solution can be written down as a metric on R4, a metric G on R4, which is Ricci flat, is actually geodesically complete, so no singularities form if you wiggle Minkowski space a bit. And moreover, in a suitable gauge, which I'll explain just in a second, the coefficients of this metric, Gij, actually converge to the coefficients of the Minkowski metric as you go off to infinity, either by staying in a complex spatial region and just waiting a long time, or actually going off to infinity in any region, in any direction whatsoever, space-like, time-like, or null. And so this theorem, of course, caused a lot of activity that continues to this day. So there's a very short list of references, but this is just references for the vacuum case, and even that list is not complete. So in a suitable gauge, let me just say one word about this. As I said, you can pull back any solution G of this equation Ricci of G is equal to 0 by any diffeomorphism of R4 in this case. And in a suitable gauge means that you have to pick sort of the right diffeomorphism in order to display this convergence back to the Minkowski metric. So why is it called stability of Minkowski space? Because the metric converges back to the Minkowski metric. Okay. So this is sort of a prototypical stability problem, and what I want to talk about now is the problem of the stability of black hole solutions. And so the main part of the talk will be in the case of positive cosmological constants. And down here is actually a picture, so in case you can type extremely fast, you can look up this video on YouTube. And it's a numerical simulation of a black hole merger. And so ultimately, once the black holes have merged, you end up with a single black hole here that looks a little out of shape. And it settles down to a stationary solution of the Einstein vacuum equation under emission of gravitational waves. And so that's something that I will try to explain mathematically. Okay, so first of all, I have to introduce the relevant black holes when the cosmological constant is positive. And that will also explain what the meaning of this cosmological constant actually is in this case. So you may safely ignore the explicit formulas. The main features that I want to point out is that the manifold now still has a time direction. That's called T star here. And the spatial manifold here is now actually a compact annulus. So it's no longer sort of infinite extent like in the stability of Minkowski space, but it's actually a spatially compact region. And moreover, the metric, again, is extremely explicit, was found in 1918 by Kotler. But again, geometrically, the picture is as depicted down there. So you again have an event horizon, which is now at r equals r minus, roughly r equals to m, like before, which has the same geometric meaning as before. But now, when the cosmological constant is positive, you also have another horizon at r equals r plus, which is typically sort of scale lambda to the -1/2. So it's extremely far out when lambda is small and positive. Geometrically, it has the same effect. But sort of physically what it means is the following. It's the boundary of the observable universe for an observer that stays in between these two hypersurfaces r equals r minus and r plus. Because anything that happens to the right of, let me actually try this thing here. Anything that happens to the right of r equals r plus, say a star explodes there, the light will not actually reach the observer that stays in the intermediate region here. Exactly because light has to follow these light cones. Okay, so there's only the spatially compact region in which something interesting might happen here. There also exists a generalization of the Schwarzschild-de Sitter family, again, to rotating black holes called the Kerr-de Sitter family of metrics, and it was discovered in '68 by Carter. But as before, all these metrics are actually stationary. There's no dynamics in there, which is the reason why you might want to study the initial value problem for slightly perturbed initial data. So you're sort of nudging the black hole and see what happens. And the theorem that I will try to explain a bit in this talk in joint work with Andras Vashi was published in 2018 concerns the stability of this Kerr-de Sitter family of black holes, at least when the black hole rotation speed is very small. And so remember, again, the initial surface sigma is this compact annulus. It includes a bit of the inside the black hole, a bit outside the cosmological horizon, just a little bit of safety margin, rappel in French, I believe. And you give yourself two pieces of initial data, gamma and k, and you assume that they're close to the initial data of a Schwarzschild de Sitter metric. So you start with a non-rotating black hole, and you perturb the initial data slightly. The theorem then states that there exists a solution of the Einstein vacuum equation, this initial value problem. So an Einstein metric, creature of G is equal to lambda times G think of it as the future of this initial surface. And moreover, we have a long-time description of this metric, namely, there exist parameters of one of these completely explicit Kerr de Sitter black holes, so some mass and some angular momentum, such that the metric actually is equal to this Kerr de Sitter metric, this very specific four-parameter family, plus a remainder term that's called G twiddle here. And this remainder term you can think of as modeling gravitational waves. This gravitational wave tail has an amplitude which is decaying exponentially in time at some rate alpha, which in principle one can also quantify. Okay, so that's the statement that Kerr de Sitter black holes, I think sometimes physicists say, have no hair. So somehow for very long times, these perturbed Kerr de Sitter black holes are just described by four parameters, the mass and, well, the angular momentum. You could reduce that to a single parameter by rotating your coordinate system even. Okay, so in terms of experimental relationships here, down here is this famous picture from the first measurement of black hole mergers. And so what's happening here is the relative distortion of some arm of this LIGO interferometer. And at roughly 0.42 seconds, I believe the two dancing black holes merge into one. And then the single black hole settles down exponentially fast to presumably one of those Kerr or Kerr de Sitter black holes. But of course, the mathematical theorem with all the small epsilons involved, how close to the initial data have to be, only describes the part of this measurement here that's probably hidden in the noise. But I will tell you some more optimistic parts later. Okay, so this is the main theorem, which I want to discuss some more. Okay, so as I mentioned, the Einstein vacuum equation is nonlinear, and you can try to solve for a metric. And there's also this diffeomorphism invariance floating around. So a very common thing to do is that you look instead at a very simple toy model, which is that of a scalar wave equation. Okay, so what we will do is we will look at an exact Kerr de Sitter spacetime, stationary, so time independent. And so we call this metric G, and we just look at a real or complex valued solution of the wave equation. So oops. Oh, this is, yeah, it's too complicated. So it's a solution of this wave equation, box G applied to phi. So it's just the standard wave operator here is equal to 0. And for simplicity, we'll assume that the initial amplitude of the wave and the rate of change of it are smooth functions on this initial surface. And then there's a complete description of the long-time asymptotics of the solution of this equation proved by Dyatlov in 2012, which states that for any real number alpha, except for some discrete set, the solution can actually be written as a possibly infinite sum over omega j's, which are complex numbers, a discrete set of complex numbers, of e to the minus I omega j t star times aj of x, plus a remainder term that decays at the desired exponential rate. So this might well be an infinite sum, so you have to be careful about convergence and so on. But importantly, these numbers omega j depend only on the Kerr de Sitter black hole under consideration. And the functions aj of x, they also do not depend on the actual precise initial data up to, of course, an overall complex prefactor. So there's some scalar constants that you could put in front and then make the aj of x completely independent of the initial data of the field. Okay, so in other words, a scalar field around a Kerr de Sitter metric has these characteristic decay rates and oscillation rates omega j, the real part and imaginary part thereof, and also these characteristic profiles aj of x, sort of eigenfunctions, if you will, associated only with the black hole itself. Okay, and there are precursors in the mathematical literature that led up to this theorem here. Okay. So where does this come from? And so this is now the first really spectral theoretic part of the talk. So here upstairs is again the theorem written in a slightly different form, just in terms of a forcing problem rather than initial data, but they're equivalent. And the key input here, so the key idea is simply the following. You have a time translation invariance, because the metric is time translation invariant. So of course, the first instinct should be that you take the Fourier transform to take advantage of that symmetry. And if you do that, then the wave equation, the wave operator, becomes the spectral family. You just replace time derivatives by multiplications by the spectral parameter, as usual. Then you have to, so the spectral family I call box hat of omega is now a family just acting on functions in the spatial domain. So you have to invert that and take the inverse Fourier transform. And so at the bottom of the slide, I write down the output of that procedure. So you take the inverse Fourier transform over some contour, imaginary part of omega equals minus alpha, just some shifted real line. And then as you shift the line up and down, you pick up residues arising from the poles of the inverse of the spectral family. So this is a very standard way in scattering theory to get asymptotic expansions. But of course, you have to justify that formula, and that's very non-trivial work. So the key input to make this work is that this resolvent, first of all, so it's easy to show that it's actually analytic far in the upper half plane, follows essentially from energy estimates. But non-trivially, it admits a meromorphic continuation to the whole complex plane. And the poles are precisely these omega j's, these so-called quasinormal modes or resonances. Moreover, in elementary complex analysis, when you do these contour shifts, you always have to make sure that you don't get boundary terms at infinity. That's guaranteed by the so-called high energy estimates, which are simply suitable polynomial bounds on the operator norm of the resolvent as you go off to infinity along this contour. So this gives you the qualitative picture here of this quasinormal mode expansion. But of course, to get more quantitative information, if you want to know, does the wave decay, at what rate does it decay, you of course have to know what the poles actually are, or at least have some sensible estimates on their location. Okay. So that much about, so here is just one picture, numerically computed quasinormal modes for a Schwarzschild de Sitter black hole. So this was done by an undergrad student at MIT of mine, Yu-Ching Shi. But of course, these have been computed in many instances, also in the numerical relativity literature. For instance, there's this fantastic review by Berti, Cardoso, and Starnets. Okay, so in this picture here, all these quasinormal modes omega have negative imaginary part, which means that the corresponding contributions in the sum are exponentially decaying, with the sole exception of omega equals 0, that's the topmost dot there, which corresponds to a stationary contribution to the long-time asymptotics of the solution. And the corresponding aj of x, this profile, is just a constant. Okay, constant solve the wave equation, and that's what you see in the long-time asymptotics here. Okay. So if one tries to adapt these ideas to the nonlinear Einstein equation, there are, of course, plenty of issues that you need to grapple with. The first one is this gauge fixing issue, that you need to get rid of this diffeomorphism action somehow. Then it's a nonlinear equation, so you somehow have to set up a suitable nonlinear iteration scheme, say. And then the last bit, you have to analyze waves not just on exact Kurdistan spacetimes, but on those spacetimes that arise, for instance, as solutions of this main theorem. Of course, this is a little circuitous right now. You have to understand waves on spacetimes that only settle down to a Kurdistan spacetime at some exponential rate. So I'll try to explain a few ideas related to all these 3 points. So first, let's just take a breath and forget about nonlinear equations after all for one more slide rather. And consider again an exact Kurdistan spacetime and look just at the linearization of the Einstein vacuum equation. So there was anyway. So in other words, we just look at a slowly rotating Kurdistan metric G, and we simply look not at the full nonlinear Einstein equation, read G minus lambda equals 0, but we linearize it just formally around this metric G. And so solutions of this linearized Einstein vacuum equation are often called gravitational waves. So very small perturbations of a given solution. So the first thing that I want to point out is that this diffeomorphism invariance of the nonlinear Einstein equation can also be linearized in one-parameter families of diffeos, and gives rise to the fact that any solution, for any vector field V, which generates by its flow a one-parameter family of diffeos, for any vector field V, the Lie derivative of the metric actually lies in the kernel of this linearized Einstein equation. So that's, in words, the statement that infinitesimal changes of the coordinate system don't carry any sort of physical significance. You can always do that, and you get another solution of the linearized Einstein equation. But sort of there is no physics underlying this. You're just changing coordinates. More interestingly, let's look at a more general solution. So that's the equation. Let's see if I can do it down here. Let's look at a more general solution of this linearized equation, and let's just assume that it's a mode solution for simplicity, because we're keeping in mind this theorem by Dyatlov, which tells you that if you understand mode solutions, you understand the long-time behavior of these linear waves. And what was really the starting point in the physics literature for black hole stability was this seminal paper by Reggie and Wheeler in the 50s, and then there have been many, many subsequent developments. We're using the one by Kodama and Ishibashi, which adapted things for positive cosmological constant. And what they have proved is the following result called mode stability for the linearized Einstein equation. Namely, it says the following. So you take yourself a frequency omega, and for simplicity, let's just say the imaginary part is strictly positive. And you're looking at a mode solution, like this one down here. And so notice that under this condition of the imaginary part, this exponentially is actually exponentially growing in time. So you're looking at a linearized perturbation of your black hole that is exponentially growing in time, and you ask, what could that be? And mode stability is the statement that any such potentially extremely damaging to the stability of the black hole solution actually is just an infinitesimal change of coordinates, a so-called pure gauge solution. So there is some vector field such that the Lie derivative of your metric along that vector field is this exponentially growing guy. So in other words, there are actually no physically interesting modes that are exponentially growing. So somehow, from a physical perspective, there is no exponential linear instability of these black holes. That also extends to purely oscillatory perturbations. And if you have stationary perturbations, there is a little bit of physically interesting stuff happening, because a particular solution of this, so a particular stationary solution of this equation can be obtained by simply wiggling the black hole parameters infinitesimally. And so then if you do that, you get what's called a linearized Curtis-Sitter metric. So you just linearize the family of metrics, the Curtis-Sitter family, in the mass or angular momentum parameter. So mode stability, again, is still an active topic of research. There were also some talks last week, for instance, by Teixeira da Costa on extremal black holes and so on. Okay, so now, of course, mathematically, there's this issue that you do have, for every complex number omega, a whole lot of mode solutions of this equation at precisely that frequency, but somehow basically all of them in the upper half plane, corresponding to instabilities, are physically irrelevant. They're just coordinate changes. So you somehow need to, if you actually want to prove a theorem, you need to get a better handle on how to capture those. So that's the most technical part of the talk. So, but 2 slides from now, it's going to get easier again. So the key thing to do is to what's called fix a gauge to eliminate this possibility of pulling back your metric by diffeomorphism and getting another solution. So that you can always do for the Einstein equation. But if you impose some extra conditions on the metric, that I'll explain in a second, this will not be allowed anymore. So more precisely, one particularly convenient way of fixing a gauge is the following. So remember that you want to find a metric on some 4-dimensional manifold satisfying the Einstein equation. Forget the metric for a second and just look at this 4-dimensional manifold and put on it your favorite metric, G0. So a natural choice would be you take G0 to be the metric, the black hole metric you're perturbing. And now you remember you want to solve the Einstein equation, so now you want the metric G to be such that a certain one form W of G, so natural choice is you take the difference of connections and take a trace, gives you one form, that this be equal to 0. So the vanishing of a one form gives you 4 extra conditions on the metric, which at least formally should eliminate the 4 degrees of freedom that you have from pullback by diffeomorphisms on a 4-dimensional manifold. And so it sounds like you made your life harder by now not only having to solve the Einstein vacuum equation, but also the gauge condition. But in fact, life got extremely nice now. And so this formulation here goes in the Riemannian literature, go back to Dennis de Turk from the 80s. Namely, you can combine the 2 equations into a single equation. So P of G is equal to 0. And what you do there is that you take the Einstein vacuum equation you want to solve, and you take a certain derivative of this one form here as an additional term. And so this del G star is a symmetric gradient, so it eats a one form, spits out a symmetric 2 tensor. And there's this extra term Q, which is a 0th order term. I'll briefly explain that in a second. But that term is completely arbitrary. The great thing about this particular combination of the Einstein equation and the gauge condition is that it's actually a quasi-linear wave equation. So it now has a perfectly well understood, at least initial value problem. And one can see, you don't have this gauge issue anymore, in other words. Okay, but ultimately, of course, we don't want to solve just some arbitrary quasi-linear wave equation, but we want to solve the Einstein equation. So how do you get back from having a solution of this equation to actually having a solution just of the Einstein vacuum equation? And that's a standard trick already used by Choquet-Brehard, really, which relies on the second Bianchi identity, which is, I remind you, a statement that the Ricci curvature on any manifold, G doesn't have to satisfy any condition, satisfies the first order differential equation, namely the divergence of Ricci is 1/2 times the gradient of the scalar curvature. So you always have this algebraic relation. And if you apply this relation to this equation, you end up actually with the decoupled second order equation for W of G, which turns out to be a wave equation. So I write it here just sort of formally as box G, Q. It depends on this particular choice of Q, which right now is very mysterious, but I'll explain in just a second. Okay, so you have a decoupled wave equation for this gauge condition, and the way it works then is that if you can arrange for this gauge condition to be satisfied initially, it satisfies a homogeneous wave equation, then it must be satisfied for all times. So it vanishes identically, and once you plug that into the equation that you just solved, this quasi-linear wave equation, you end up with having solved the Einstein vacuum equation. Okay, so that's the very rough way that this de Turk trick works. Now, what about this Q here? So to explain this, just imagine for a second that you are a numerical relativist, which I myself am certainly not, but you can dream. And so suppose your initial data actually are, they have some numerical errors. So in particular, they might not actually exactly satisfy the gauge condition, and they might not exactly satisfy the constraint equations that I briefly mentioned. And now if you evolve your spacetime by solving this quasi-linear wave equation here on your computer, it might be that these numerical errors propagate and grow out of control very quickly. And what this choice of Q does is that it actually gives you an automatic damping mechanism for such numerical errors. So more precisely, what one can, so this was first suggested in the numerical relativity community by Brodbeck and Gundlach in around 2000, and then with Vashi we proved that it works in a particular manner on Kurdistan black holes. So concretely, what one can do is one can choose this particular term Q here, so that solutions of this wave equation that governs how the gauge condition propagates, whether it remains satisfied, that the solution of this equation automatically decay exponentially in time. So for numerical purpose, this sounds like it should be very useful. Okay. So that's constraint damping. That's the role of Q. And now you can forget Q if you like. Okay, so now we're faced with solving this nonlinear equation here. But again, let's first just look at the linearization and try to see whether this combination of the Einstein equation with the gauge condition leads to a better behavior of the quasi-normal modes, these particular frequencies, omega, that arise, that appear in the long time expansion of waves on this background, like in Dyatlow's theorem. Okay, so we look at the linearization of this nonlinear equation around the Kurdistan metric we're interested in, or the Schwarzschild-de-Sitter metric if you want. And what one can now deduce is the following. So look at the mode solution of this linear equation. So a priori, there's a chance that somehow the contribution from the linearized Einstein equation and from the gauge condition somehow are both non-zero, but they cancel in some magic manner. However, with the constraint damping, you actually have much better structure, because you see, you have a solution, so say an exponentially growing solution, let's say imaginary part of omega being positive, of this linearized equation. What you automatically know is that such a perturbation has to satisfy the gauge condition, because it satisfies a certain wave equation for which we know solutions decay exponentially in time, but the input here itself is exponentially growing in time, so something can't be both at the same time unless at 0. Okay, so you automatically have this extra piece of, so this extra equation basically satisfied by these exponentially growing mode solutions. And then you can appeal to the results from the physics literature and deduce, well, exponentially growing perturbations of the linearized Einstein equation are actually pure gauge. So they're sort of physically not interesting. And you can even go one step further and say, well, in addition, they're not just pure gauge, but they actually satisfy my gauge condition. And that turns out to actually pin down the possible set of offending quasi-normal modes omega to a discrete set. In particular, there are only finitely many corresponding to exponential growth. Okay, so in other words, in a nutshell, some of this introducing a gauge condition and arranging for constraint damping has reduced the, at least this formal spectral analysis of the linearized problem, basically to the physics literature studied case of mode stability, except for a finite a discrete set of possible offenders, namely pure gauge solutions, which just so happen to still satisfy the gauge condition as well. So it's not completely eliminated the diffeomorphism variance, but sort of most of it. Okay, so with that in mind, the idea then to solve the nonlinear equation is the following. So rather than solving for the metric all in one big go, you separate your task into bits and pieces. So you expect that the metric, following this linear analysis, that the metric actually should, up to some gauge issues, should decay to a Kurdistan metric with some parameters m and a, up to exponentially decaying remainder term g twiddle. So in the Dyatlov theorem, there was actually this possibly infinite sum of modes, but if you solve a nonlinear equation, try to keep track of as little as you must. So we're just ignoring all these infinitely many quasi-normal modes and just keep track of a little bit of exponential decay. So this alpha decay rate is just a small positive constant, in other words. And then we solve the Einstein equation in the form that I just wrote down, not just for the metric in one go, but in fact for the black hole parameters separately, and separately for the gravitational wave tail. And there's this extra bit theta here, which I'm not going to discuss in detail, but it allows for a little bit of flexibility in the gauge condition to eliminate these finitely many offending quasi-normal modes that I mentioned. Okay, so ignoring this gauge modification business, which is conceptually crucial, but goes beyond the scope of this talk, how do you then solve indeed this nonlinear equation, taking advantage of the information that we have gleaned from the linear theory via spectral theory? Well, you're faced with a nonlinear equation, for something living in an infinite dimensional space, but you can still imagine that you use a Newton iteration, which is a very fast converging scheme. So more precisely, we use the so-called Nash-Moser iteration. What that means is that you have a current guess as to what the nonlinear solution should be, G sub k, but it might not quite satisfy the nonlinear equation you're interested in. So there's an error term here, P of G sub k. It's a small error term. And you want to correct this error by solving a linearized equation. So you linearize around the current guess and find sort of the linear increment that you need to do in order to arrive at a more precise, so sort of quadratically more precise solution of your nonlinear equation. And the key point here is that if you use this sort of iteration scheme, then you have to solve a linear wave equation with some non-trivial right-hand side, but a linear wave equation globally at each step. And that's exactly what spectral theory is very good for describing global phenomena, so here global in time. And the expectation from what I explained about the linear theory is that the solution of this linearized equation here takes the following form. So up to these now finite dimensional gauge issues, which I'm throwing out the window, the solution should have a contribution from the zero mode, stationary, which I already said would be you take your current black hole parameters and you just modify the mass a little bit and the angular momentum a little bit. So that's m dot and a dot. And then there's the remainder is exponentially decaying at some small rate, alpha positive. And then you say, well, probably the final black hole parameter should be the sum of my current guess and this linearized update, m dot, a dot. Okay, so that's the expectation. You, of course, have to prove that this is all consistent. But if you believe this, then each metric that you have, so each metric on your space-time manifold has the form of an exact Kurdistan metric plus an exponentially decaying remainder term. Okay, so in other words, what you have to study in order to make this sort of iteration scheme here work is not just wave equations on some exact stationary background where you can just take the Fourier transform, but you have to understand solutions of the wave equation, so regularity and decay, on this sort of time-dependent but asymptotically very well-controlled, very particular background. So remember that the operator P was a wave operator, so quasi-linear wave equation. So the linearization can be thought of as just a linear wave equation on this dynamical but very particular background. And so H would be a symmetric 2 tensor, but imagine just it's a scalar wave phi, if you prefer. Okay, so if you're faced with a wave equation on a time-dependent background, your first instinct might be, well, spectral theory goes out the window because I cannot Fourier transform. But of course, that's too naive to be a useful perspective. Rather, spectral theory still will describe the long-time behavior of solutions. So this sort of half of what a function space captures on a non-compact space, decay or asymptotics. But the other half, you have to study via different means, the other half being regularity. Okay, so at this point, spectral theory doesn't become one size fits all anymore as it was for stationary problems, but now it just becomes half the story. And the other half will be understanding regularity. And I'll try to explain how the two fit together. How much time do I have? It's hard to read from here. How much? 20 minutes. Okay, thank you. Okay, and so the way that we analyze regularity is via microlocal analysis. So it used to be the main title of the talk. Now it's compressed to 2 slides. That's the way of life. So what is microlocal analysis, very roughly speaking? So the extremely brief crash course here. So it's the analysis of mostly linear PDE, but also in the nonlinear realm is very much used, in phase space, so in the cotangent bundle. And so underpinning it is the very close connection, which makes it very attractive and gives connections to other fields, especially dynamical systems, for instance. A connection between linear partial differential operators, let's say, and Hamiltonians for classical mechanical systems. And so the relationship goes as follows. So let's take the wave operator as our main star. And the principal symbol, that's the relationship of the wave operator, is a function. So imagine energy function on phase space, which I call capital G here, which at a space-time point z and space-time momentum zeta just gives you the squared length of that momentum vector. Okay, so that's piece number 1. Keep it in mind, shelve it. Piece number 2 is the notion of microlocal regularity of solutions. That's the following. So take a distribution phi on your manifold M. Imagine M is just an open set in Rn, if you like even. And I'm interested in describing what it means for this distribution to be in some sublat space Hs, locally near some point Z0. That's extremely well understood, of course. You just take a cutoff function, chi2, to a small neighborhood of this point. You multiply your distribution with it, and you ask, is it in Hs or not? How do you check Hs membership? You take the Fourier transform and ask for membership in a particular weighted L2 space, by definition of sublat spaces. Right, so here's the weight, and here's the localization in space and the Fourier transform, and you ask for membership in some L2 space. Microlocal regularity simply asks for something more precise, namely you don't only have the point where you're interested in, but also a momentum vector zeta naught, or really the direction in which zeta naught is pointing. And what you do is you cut off the Fourier transform in a conic neighborhood of this vector zeta naught. So you're just basically checking whether amplitudes of my localized distribution phi that sort of point in a particular direction have decay or not. Okay, and that's the honest definition of microlocal S-regularity. And then to combine these two things, it's a famous theorem by Duster, Martin, Romander from the 70s. It's called usually propagation of singularities, but if you're an optimist, it's propagation of regularity in the other direction. And it states that solutions of the, say, linear wave equation here are regular outside of the light cone, so the so-called characteristic set where G is equal to 0. But inside the light cone, that's the interesting part where something's happening, regularity, in the sense of microlocal HS regularity, actually propagates along the flow of the underlying classical Hamiltonian system. So here's the Hamiltonian vector field H sub G, just written down what it is. So it gives you this beautiful connection between regularity of solutions to linear PDE, let's say, and the dynamics of the underlying classical Hamiltonian system. Okay. So how does one use these sorts of techniques for the study of waves on asymptotically curved de Sitter spacetimes? So there's one extra bit that I will very roughly explain. So in this Kurdistan setting, of course, we're interested not just in local regularity of waves, but in global regularity, so uniform estimates as time goes off to infinity. And infinity is always much closer than you think, so it's always good to make it part of your manifold by compactifying. That has been a very popular thing to do in well, lots of fields, mostly elliptic PDE and moduli spaces and singular elliptic equations and so on. But it's also very useful in this hyperbolic world. So here in this picture, I sketch how you compactify at t star equals infinity by just attaching t star equals infinity sort of to your manifold with a particular smooth structure. So here I'm using an exponential compactification. What happens then is the following. So the dynamics, so the flow of this Hamiltonian vector field associated with this energy function G, the dual metric function, actually displays very interesting behavior as you when you work on this compactified picture. Okay, so the way it works is that you first start out at t star equals 0, where you have initial data. You can just happily propagate. You're just in a regime of finite time. You propagate using Dirichlet-Hermander, and everything's good, and that's it. But if you want to get uniform behavior, then you have to understand the uniform behavior of the Hamiltonian underlying system. And so in this figure here, there's one particular example of what can happen. So this vertical line here is the event horizon of the black hole. So this was called r equals r minus many slides ago. And if you're an observer with a laser pointer who falls into the black hole and turns on the laser pointer just as you cross the event horizon, then the light from that laser pointer is going to get stuck on the event horizon and doesn't escape anywhere. If you turn the laser pointer on just before you cross the horizon, then actually the light can escape. If you turn it on too late, then your laser pointer, the light emitted by it, and you all suffer some fate. Okay, so in other words, you have this sort of unstable dynamics here. And if you take this to the conclusion here in the compactification, you end up having a saddle point for the Hamiltonian dynamics at the point where the pointer was just now. So here you have a saddle point, right? You go in, and then from there, in phase space, you go to the sides. So you have critical sets for the Hamiltonian vector field. And so there then also exists sort of black box result in microlocal analysis that tell you if good regularity comes into a critical set, then good regularity comes out, very roughly speaking. And there are also other very interesting phenomena like trapping and invariant manifolds, normally hyperbolic trapping, somewhat closely related to the plenary talk by Viviane Baladi on Tuesday, actually. And the upshot ultimately is then that all points in this characteristic set are ultimately controlled by data at the initial surface. And the upshot then is that you can control regularity of solutions globally by just using these qualitative properties, mostly, of the Hamiltonian flow. So it's an extremely sort of pretty geometric picture. Okay. And very briefly, the combination, this is perhaps a bit too technical now, but roughly speaking, you can combine a priori estimates for regularity using microlocal analysis and for decay using the Fourier transform for the stationary model into a single sort of functional framework, which tells you that the linear operators in question are Fredholm between certain weighted function spaces. So Fredholmness here comes about by the usual sort of Rayleigh theorem on non-compact spaces. We have an improvement both of regularity and in weight, and that gives you compact inclusions. Okay, so this non-elliptic Fredholm theory has been very popular also in the QFT, some parts of the QFT community, for instance, by work of Girard, Rochna, and others. And also in dynamical systems by Dyatlov-Zworsky, for instance. Okay, so the summary of insights from this discussion so far is that we can combine this robust and sort of dynamical and very geometric analysis of regularity using microlocal techniques and spectral theory for the sharp control of asymptotics and decay to solve these linear wave equations on time-dependent backgrounds. And then you can put this together with a nonlinear iteration scheme to solve nonlinear equations. And if you solve the Einstein equations, there are these extra Einstein-specific problems that you have to deal with. So you have to find a suitable gauge condition, arrange constraint damping, and so on, so that the required spectral theory, so really just this very particular small part in some sense, finding out what mode solutions exist, reduces basically to the mode stability results from the physics literature. So it's somehow very attractive from that point of view. Physicists always claim, I mean, this is an exaggeration. But if you have mode stability, then the black holes are stable. And it turns out that this is sort of true once you add all this extra mathematical baggage. And you can also find the space-time parameters and suitable gauge conditions as part of the full iteration scheme. Okay, so for lambda equals 0, the results are much more incomplete. And so how much time do I still have left? Oh, wow, excellent, okay. Relativistic effects make me speak faster. Sorry? Okay. Okay, if I speak extra fast, then I can make it 15. Okay, so for lambda equals 0, the results are more limited, as I said. But I will try to follow roughly the outline, the steps from the discussion of lambda positive. So what is the difference, the simplest geometric difference when lambda is equal to 0 and you're looking at a Ricci flat spacetime? Well, the spacetimes that I'm interested in here are asymptotically flat. So remember the Schwarzschild solution was, so here I'm drawing it slightly differently, time coordinate and then some spatial manifold sigma, which you can think of as R3 with a ball removed. So it's non-compact. It has the asymptotic Euclidean infinity floating around. Okay, and so Kerr was the generalization of Schwarzschild to have angular momentum. The nonlinear stability problem, so the analog of the theorem that I talked about in joint work with Vashi, for subextremal Kerr black holes is still open in general, but there has been significant recent progress. In particular, this year, just a few months ago, there were 2 preprints, one by Defermos-Holtz, Rodniansky, and Taylor, about the nonlinear stability if the initial data are constrained to a suitable 3 codimensional submanifold of data, gamma and k, and work by Scheftel and Kleinerman, which we will hear about tomorrow, in fact, in Jeremy Scheftel's plenary talk. So stay tuned for that. But just to follow the outline, as I said, let's just look at the very simple case again of just the scalar wave equation for a complex valued function on a subextremal Kerr metric or the Schwarzschild metric if you want to have a metric for which I actually gave you the formula. So now the initial data I assume again to be smooth, and because the initial surface now actually has it's non-compact, it makes sense to also impose compact support for utmost simplicity. Of course, some quantitative decay and regularity is always enough for anything. The asymptotic behavior of solutions was then, so at least an upper bound was fully resolved in a paper by Defermos, Rodniansky, Schlappentoch, Rothman in 2006, so appeared in 2016, and combined with a sort of black box result by Tataro from 13, you get the following result, namely waves do not have any more this expansion into quasinormal modes and exponential decay, but they merely have inverse polynomial decay. Yesterday's talk by Stefanos Aritakis was also a lot about these sorts of decay results. Okay, so you have inverse cubic decay if you remain in the vicinity of the black hole, let's say. And this sort of finished a long series of work, starting with work by Kay and Wald in the 80s in the sort of math physics literature on understanding decay of linear scalar waves on black hole backgrounds. Okay, so also as discussed yesterday in Stefanos' talk, one can do more. And so before I actually read this out here, a conjecture that should be easy to prove but has not been written down is that, in fact, solutions of the linear wave equation on Kerr, subextremal Kerr, have actually a full asymptotic expansion, but not into exponentials, but into inverse powers of the time function and perhaps some logarithms floating around. So this, with techniques available today, this should be easily doable. But what's been proved and posted on the archive is this theorem here, which I proved in 2020. And Angelopoulos, Aritakis, and Gajic gave a completely different sort of physical space proof of this fact. Namely, the solution doesn't only decay inverse cubically, but in fact, there's a leading order term to the asymptotics. So there's some constant c, such that the difference of your wave and c times t to the minus 3 has almost a full order of decay more. And this constant c is just given explicitly by some integral of the initial data against something. Okay. And the spectral theoretic perspective, again, an analogy to the Curtis-Iter setting, is the one that I espoused in my preprint. And so again, you just take the Fourier transform of the, no, it's gone. You take the Fourier transform of the wave equation here and end up with a spectral family, again, some family of operators now, which you can roughly think of as the spectral family of an asymptotically Euclidean metric in 3 dimensions. And so this sort of resolvent has been studied at least since, so the most interesting part of it, the low energy regime, has been studied at least since the 70s by Jensen and Kato, precisely for the purpose of understanding long-time behavior of solutions to Schrödinger or wave equations. Okay, so concretely what one can show is that the resolvent, so the inverse of the spectral family here, is again analytic far up in the upper half plane. It actually extends to an analytic function in the, operator value function. In the full upper half plane, so meromorphy is very easy to prove. Analyticity just requires you to exclude the possibility of mode solution. So that's sort of a pointwise algebraic statement in some sense. So we use Whiting's mode stability result from '89 for that. As far as shifting the contour is concerned, high energy estimates you can also prove all the way down to the real axis. But the crucial new feature now is that, so first of all, you cannot expect a meromorphic continuation to the whole complex plane. And second of all, relatedly, because the resolvent actually has a non-algebraic singularity at zero frequency. And so concretely what you can prove is that the resolvent here is something smooth, plus this is the most singular non-algebraic term. There's a logarithmic singularity, omega squared log omega, and there's some explicit rank 1 operator pi 0, whose range consists of constants, so that's where this comes from. Okay, so that means that this picture is sort of much less ornate here. You just have the upper half plane. You can shift the contour all the way to the real axis, and you pick up the long-time behavior of the solution of the equation from a non-algebraic singularity of the resolvent at 0. Okay, so that's the story for scalar waves. For the linearized Einstein equation, one can also, again, work on exact Kerr and try to see how far these spectral theoretic methods can get you. And so in the interest of time, let me make this a little bit shorter than written down. But roughly speaking, you again look at the gauge-fixed equation and look at the linearization thereof. But if you don't like gauge fixing and so on, you can just imagine if you don't like this de Turk trick, you can imagine you just solve the linearized Einstein equation, linearized Ricci is equal to 0, with a particular gauge condition that I could tell you what it is. And so you start with certain initial data for your linearized Einstein equation, roughly speaking. You solve the linearized Einstein equation. So in other words, you look at gravitational waves and their decay on Kerr spacetimes. And what we prove is that in a particular gauge, the solution indeed has a very similar structure to the Kerr de Sitter setting. First difference, of course, the remainder term is now polynomially decaying, inverse polynomially, rather than exponentially. A similarity is that you still see this infinitesimal changes of the black hole parameters. Okay, so so when the black hole sits there and you perturb it by gravitational waves coming in, the black hole might infinitesimally gain some mass or angular momentum, and so on. And then in the particular gauge that we work in, there's an extra possibility, sort of akin to these finitely many exponentially growing modes in the Kerr de Sitter setting that are pure gauge. There's an explicit possibility that you also change your coordinates infinitesimally by flowing along a particular vector field. And in fact, we show in the gauge that we use that these vector fields are actually highly constrained. They lie in a particular 6, or if I didn't lie, 7-dimensional vector space. And they correspond to translations and boosts of the coordinate system used to describe the black hole. The proof is spectral theoretic, so here it's one line, but in reality, of course, it's quite a lot of work. But you show that there's an explicit second-order pole corresponding to bound states, first-order pole corresponding to bound states and half-bound states, and then a particular remainder with a certain regularity. But from the point of view of thinking about a nonlinear problem, this is quite attractive, though definitely not the desired statement yet. But you can read off the change of black hole parameters in response to incoming radiation. You can read off the gravitational wave tail h twiddle, and you can also read off how the black hole in the particular gauge that one is working in wants to respond in terms of how to, it might somehow move its center of mass a little bit and go off in a particular direction. It turns out for the nonlinear problem, this is not precise enough for sure. So one at least needs to capture sort of more refined aspects of this gravitational wave tail that I don't want to get into now. A different approach to proving sort of the same result under somewhat more restrictive assumptions was obtained by Anderson, Bechdel, Blue, and Ma in 2020. And the linear stability of the Schwarzschild family of metrics was proved prior by Daferma, Soltag, and Rodnjansky. And there are also many works using sort of different gauges, mostly in the Schwarzschild setting, but also concerning sort of scalar aspects of the linear stability problem regarding the so-called Tucholsky equation. So this is still an extremely active area of research. And so, for instance, the stability of sub-extremely curved black holes under linearized perturbations has not actually been proved. Okay, so where is this headed? The obvious thing that I omitted in my discussion of lambda equals 0 is, besides, of course, the nonlinear stability statement, is the microlocal framework for asymptotically Kerr metrics. So what's the correct compactification on which the Hamiltonian dynamics for the associated metrics have suitable behavior and sort of well understandable critical sets and invariant sets and so on. And that, of course, has to fit neatly with the spectral theory. Another rather different open question is the stability of fast-rotating Kerr-de-Sitter black holes in the nonlinear regime, where there's definitely a chance that one could do this. What's missing is the rigorous proof of the mode stability result of the sort of physics literature kind. There is some progress by Casals and Teixeira da Costa, but it still doesn't close the gap. Another interesting thing, perhaps also to connect mathematics to what's observationally doable, is that one might try to actually obtain a full quasi-normal mode expansion of these nonlinear metrics arising as solutions of the Kerr-de-Sitter stability problem. So you want to somehow show that the metric is not actually just exact Kerr-de-Sitter plus exponential decaying, but perhaps you have an expansion into at least a few or infinitely many quasi-normal modes, like in Dyatlov's result, up to an error term. Of course, as stated, this can possibly be true because you will expect some nonlinear mode coupling and there might be some multiplicities and so on. But I've been told by Vitor Cardoso that apparently one can actually measure some of these omega j's, so some of these low-lying resonances with 10 or 20% accuracy already from observational data. And the last thing is sort of a little bit more mysterious, perhaps. So typically, black holes are modeled out there in the universe by the Kerr metric, not the Kerr-de-Sitter metric, the positivity of lambda notwithstanding, but that's sort of an extremely large-scale phenomenon, whereas the black holes are not that far away. And what they measure there, so for instance, as in this private communication by Cardoso, is that they actually do see an exponential decay with some oscillations. So you have this quasi-normal mode expansion for short times, and then everything else is hidden in the noise. But mathematically, we know that solutions on Kerr only have polynomial decay, inverse polynomial decay at best. So how do you make sense of an asymptotic expansion that starts off with something exponentially decaying plus a polynomially decaying remainder term? So there are some works in this direction by Dyatlov and Garich and Warnick, but there's still definitely a lot to understand there. Okay, thank you very much for your attention.
Thank you very much for this nice talk. So are there questions here in the room? Yes, please.
Yes, thank you very much, like to all of us, for a wonderful talk. I have two things. One is a comment, and the other is a question. Okay, the comment is, I think I understand that your vector field, capital V, which you introduced in the last slides, the capital V.
Sorry, yeah.
It's at the end. You had a Lie derivative with respect to V. Right, exactly there. Right, that this is to capture the recoil of the black hole due to the emission of gravitational waves. That is, the black hole cannot, the final black hole, let's say, the outcome, cannot be stationary, cannot be motionless relative to the initial center of mass frame, because some radiation has been emitted, therefore there is going to be a recoil in the opposite direction. This is what this captures, right?
Yeah, so this V here is really a sort of a stationary correction to the center of mass, but what I'm hiding here is that in this decaying tail here, there will be further corrections that for the nonlinear problem one has to take into account, which account for what you're saying, that the black hole actually doesn't just sort of shift and that's it, but actually it might settle down to a sort of a different center of mass at sort of, at some particular inverse polynomial rate, which has to be regarded as leading order still and sort of not, you cannot swipe it under the rug as I'm doing it here, But for the nonlinear problem, you really have to capture precisely the way that the black hole might settle down to its final center of mass.
Yeah, but that black hole will be moving relative to the initial one. So this must be partly captured by the second case, the asymptotic boost, in the case of V, right? I would think.
Yeah. Yes, indeed. So, yeah, if you want to, so sort of a reverse way, perhaps, of thinking about this is if you really insist on keeping the black hole where it used to be, you can also boost your initial surface a little bit, and I mean because momentum will get radiated away, and so you can boost your surface in the opposite direction, and thereby make sure that the black hole actually doesn't attain final momentum. Yeah.
Okay. Now the question is, in this analysis, where is it that the following fact is reflected, namely that the Kerr black hole, the horizon of Kerr, is surrounded by the ergosphere, a region where the killing field, which is time-like at infinity, I'm talking about the case of zero cosmological constant, but there is something corresponding. Where is it reflected that there is a region surrounding the horizon where the killing field, which is time-like at infinity, the d by dt, becomes actually space-like? This should be somewhere reflected in your analysis, right?
Right, but it's actually, so it turns out to play actually an extremely small role because, so this is not based on sort of energy methods where one actually tries to find some replacement for the dt energy, which is not coercive. But instead, let's look at the, okay, let's see if I can find a good example here. So, the only thing actually that happens when you turn on angular momentum, so if you have no angular momentum and you look at the spectral family, then actually this box hat of omega is actually elliptic in the whole black hole exterior region. And it degenerates in a particular manner at the horizon. If you turn on angular momentum, it just turns out that in the exterior region, indeed, it is no longer elliptic, and precisely it fails to be elliptic in the ergo region. However, so if you, okay, so that's number one. But number two is that, so it's convenient to actually analyze this spectral family on a slightly larger domain, because at the event horizon something interesting is happening, so it's nice to include it in the interior of your spatial manifold. And so from that perspective, already on Schwarzschild, actually the spectral family is not elliptic anymore because it degenerates at the horizon, becomes hyperbolic on the other side. And so there's already some sort of non-elliptic propagation of singularities sorts of statement going on.
Borderline.
And the ergo region, the only thing that happens is that now the, I hope I get this right, the unstable manifold of the conormal bundle of the event horizon, it turns out that's sort of the, that's those photons that get stuck to the event horizon. The unstable manifold of this actually just goes a little bit into the black hole exterior region, the ergo region, before falling back into the black hole. So in the phase space level, actually, it's not a big difference. It's not a difference at all. So the dynamics, the Hamiltonian dynamics, are actually just the same. It's just that the projection to the base of the characteristic set, so the light ones, just suffers this particular fate that it intersects the exterior region non-trivially.
I see. Very clear, yes.
It's very similar also. So the normally hyperbolic trapping is very similar in some sense in spirit, because on Schwarzschild the photon sphere is just in physical space actually hypersurface. But if you regard it as location and momenta of the photons that get stuck, it's a symplectic manifold. And if you so it's a submanifold of the cotangent bundle. And if you perturb to Kerr, it remains such. It's still perfectly smooth, codimension something. Submanifold of the cotangent bundle with exactly the same normally hyperbolic structure. The projection to the base is terrible, but that's irrelevant from the point of view of microlocal techniques.
I understand. Very good. Yeah, excellent. Thank you.
Are there other questions here in the room? Yes, please go ahead.
Well, perhaps it's obvious, but it's a small comment about your last point in the open questions. So I think this is exactly what happens in quantum mechanics when you have a metastable state, right? That in physics we always say that it decays exponential with some decay rate, but strictly speaking, you always have a power law tail under it. So if you wait long enough, so.
Yeah, so I mean, there are some similar results in the math literature. I think some works by Einstein and other people suffer. So for that, you sort of need an extra scale that somehow breaks the. I mean, right now there's there's no extra scale that you can somehow use to separate exponential decay versus polynomial decay. For instance, the polynomial decay came with a tiny prefactor, for instance, then there would be some time scale in which clearly the exponential decay would be dominant. And so one has to somehow think about appropriate settings where one gets this extra large or small parameter. So Dyatlov's result is for initial data with very high frequency, so that are localized at very high frequency. And then in fact, the exponential decay is dominant until a time of sort of log of that frequency. And only then does a polynomial tail take over. So that's a particular setting in which one can make sense of this. Yeah, thank you.
There are a couple of questions online. I can just read what I received. So what if we had a naked singularity? Would it become unstable and transform itself into a black hole?
I am unable to answer that question. So naked singularities have been studied, of course, by Christodoulou in the 90s, and there is some recent work by Rodniansky and Schlapp-Rothman about them, but even their construction is quite challenging. And typically, they appear to be unstable, so horizon tends to form upon perturbation, but in general, I cannot say anything, I'm afraid.
There is the second online question, which I'm also going to read. So is there an ultraviolet cutoff implied in the initial data due to the quantum gravitational effects? Would it affect the stability conclusion?
So if I attempt to reformulate that, so mathematically, of course, so I didn't specify that. So I say here the initial data are close to the initial data of a Schwarzschild de Sitter metric. That's meant in a particular function space that encodes, so that demands that not only sort of pointwise are these tensors close, but also with the 20 derivatives, are they close pointwise? And so in that sense, some of the initial data indeed have very small high-frequency contributions. So sort of there's of course the mathematical question: what happens if the initial data are rougher? And so so in the black hole stability context, I have no idea how low you can go. In general, it's a theorem by Kleinerman, Rodniansky, Sheftel, this L2 curvature conjecture, that you actually have a well-posed initial value problem under extremely weak assumptions on the initial data. That guarantee at least the local existence of a solution. But as far as black hole stability is concerned, how low you can push regularity, I don't know. So that's my reinterpretation of your question. As it stands, of course, it's just a purely classical gravitational problem here.
Sure. Okay, so let's thank our speaker again. We don't have much time.
Thank you.
I suggest to have a short, maybe 5 minutes break before the start of the next session.